Hi, this is Cross.Nabla, and today we are going to be going over section 11.5, lines and curves in space. So what we've been going over in these past couple of sections have been what vectors are in 3D space and some vector operations like the cross product and dot product. And in this section, we're actually going to start applying it to more general 3D curves and lines. We're going to start off with lines because it's the more basic example, but then you can generalize it to any and all curves, right? So as we can see this right here. A 3D curve can be given parametrically by x equals f of t, y equals g of t, and z equals h of t, where t is on some interval I, and f, g, and h are all continuous on the interval I. We can specify the curve by the position vector r of t, and we can see r of t with the little arrow here. In our previous videos, it was bolded, so it's hard for the viewer to see, but now to actually arrow, it's convenient for us. F of t I hat plus g of t j hat plus h of t k hat. And what we can do is we could also write this in our other vector form like this. So that's another way we can write it as well. And it's going to be useful for us actually when we're writing it for taking the derivative of it, which we'll do later on. And going on to the next section, given a point P naught determined by the vector R naught and a vector A I hat plus B J hat plus C K hat, the equation R equals R naught plus VT determines a line passing through the point P naught at T equals 0 and heading in the direction determined by V. A special case is when you are given 2 points on the line, P naught and P1, in which case V, the vector V that determines the direction, is equal to this. And for example, let's say we have a point at the origin right here. Let's say we have a point up in space right here, right? So if I extend out this line further, we're going to call this at the origin 0, 0, 0. And let's say we're going 1, 2, 3, 4, 5, 6 in the negative x direction, but we go 1, 2 in the y direction, and we go up 3 in the z direction, we can see that the vector that's being formed, this line, we can determine what it's going to look like. And what we can say is that this is going to be something -6, 2, 3. And we can actually determine this from the special case. We can do the special case real quick actually, where we go -6 in the I hat direction, our x, we go +2 in the j hat direction, and we go +3 in the k hat direction on this interval for r prime of t, right? And another thing that you're going to have to add is that this is not the entire function. This is only a part of the line, right? Because if we were to put like something like t r of 100, right? That doesn't fit on the green line shown right here. So what we have to do, in fact, is we have to actually bound this by saying that t is an element from 0 to 1. And this is a branch of mathematics called set theory. It's not really relevant. Set theory is not really relevant to this video, but it's important to make sure that you bound your vector valued function as we're going through this, because it's going to make sure that we're not going to blow off into infinity, right? So, and the reason why it's going to be from 0 to 1 is because we plug in 0 into this function, we get 0, 0, 0 is our point, and we get r of 1, we get -6, 2, 3. And here are some other ways you can rewrite the vector expressions. It's kind of what we did earlier for this first example right here. And looking at this is another form of writing it too. And like what we did in calculus 2 with parametric functions in 2 variables, this is an extension of this into 3 variables. A, B, and C are your direction vectors, like here, here, and here for this. And now, example 1, given that we just did the example above, feel free to pause the video and try this on your own. So find the equation of the line segment from 2, comma, -1, -5 to 7 to 7, -2, -3. Okay, so how much are we going in the I hat direction? Okay, so you're doing 7 minus 2 I hat plus how much in the j hat direction? So we're going to go from -1, comma, we're going from -2, comma, -1 j hat plus -3, comma, -5. You go right minus left. And in this case, we can get 5 I hat plus 5 minus j hat plus 2k hat. However, this isn't our final answer. These are only our direction vectors for A, B, and C, right? So we know that we can just call this R. And if we're trying to solve for R of t as a function, we can use this as a starting off point. We can say that we can use our initial point. Let's just say our initial point was 2, comma, -1, -5. We do plus t times the direction vector R times t, where t is an element from 0 to 1. This helps us determine the line, right? And we can look at this and we can plug in 0 and 1 at our endpoints. So we could do is plug in 0 here, and we can see it's going to give us back 2, -1, -5. Plug in 1, we're going to get 7, negative. We're going to get 7, -2, 2. 7, -2, and 3. Yep. And another way we can eliminate the parametric like we did in Calculus 2 is we can write these symmetric equations. And these symmetric equations are given in this form, and you just have to isolate to solve for t, and you can set them all equal to each other, right? So for this example right here, write the symmetric equations for the line through -2 to -2 and parallel to 7, -6, 3. One thing I like to say before I do this example is that this right here refers to a point in space. It's not a vector, it's just a point in space, right? It's a dot in space. And this represents the direction of that point in space, right? It's a little bit confusing to think about at first, but given this example, it will make sense because we have a line that goes through the point and it's going to be parallel to that, right? So first thing we can do is write our equation R of t equals -2 to -2 plus t 7, -6, 3. And then we can rewrite this into its separate vector components like we did before. And now we can say that it's going to be -2 plus 7t, 2 minus 6t, -2 plus 3t, right? And then we can say that we now know that it's going to be x equals -2 plus 7t. And we can isolate for t now. We can say that x plus 2 divided by 7 equals t. We know that y of t equals 2 minus 6t. So y equals 2 minus 6t. So we can do y minus 2 divided by -6 equals t. We don't have to simplify it for this case, but it'll just save us time for now. And then we have -2 plus 3t equals z. So then we do z plus 2 over 3 equals t. And now we can actually set these all equal to each other. So it would be x plus 2 over 7 equals y minus 2 over -6. And if you want to simplify, you could just do it like that. It doesn't really matter for the sake of this problem, though. And then z plus 2 divided by 3. So we just removed the parameter t, and now you have symmetric lines for all three coordinate directions. And now for example 3, I forgot to remove the symmetric part from this, but it's just we're just trying to find the equations of the line through the point -5, 7, -2, and perpendicular to both vectors right here. And one little hint before you guys can pause the video and try to solve this. When we're given a we're given something that's perpendicular to two separate vectors, the operation that we would use would be the cross product, because the cross product from 11.4, when we went over that, talked about how vectors in 3D space, if you were to cross them, you get a perpendicular vector. So we can go over that real quick again, where you have a vector lying in space right here and a vector lying in space over here. The resultant vector, when you cross them, points orthogonally. It gets you it's orthogonal to both the red and blue vector in that case, right? So you would use the cross product to solve for that. Feel free to pause the video now as you want to try this on your own. Okay. So I think what I'm going to do first is I'm going to solve for the vector that's normal to both this and this. And the word normal just refers to 90 degrees, or like tangent, right? So in this case, we can just apply our cross product rules. So it's going to be I hat, j hat, and k hat. 3, 1, -3, 5, 4, -1. And we just apply the rules that we learned from the previous section, which is just going to be 1, -1. So it's going to be 11 in the I hat direction. And then we have okay. And then for our z, we have okay, so now we have our vector that's tangent to both of them. Actually, sorry, not tangent, normal to both of them. So that's our direction, right? And then we can plug in our points. We can plug in our point now to solve for this. It'd be r of t equals should be +7. Yeah, +7. And that's our resultant answer. And now that we have this, we have example number 4, trying to find the equations of the lines of intersection between the planes x plus y minus z equals 2 and 3x minus 2y plus z equals 3. Now this one involves a similar thing that we did in the previous problem with the cross product of the two planes. And before you guys can pause the video, what I would say for the setup of this is that these planes, they're going to be perpendicular at the point of intersection. So that's where the cross product will come in, right? So in this case, it'd be 1, 1, -1, because right here we can think of this as our I hat, our j hat, and our k hat. We can think of this as our I hat, our j hat, and our k hat. Right, so in this case, it'd be 3, -2, 1. And now given this, I like you guys to try and solve for the line of intersection between these respective planes. So feel free to pause the video now, try that on your own. Okay, now looking at this one, just another cross product. I'll make this a little bit bigger so it's easier on myself. 1, 1, 1, 1. -1, 3, -2, 1. Okay. So then we're going to get 1 times 1 minus 2 times -1. So then it's going to be equal to -1. So then we get -1 times 1 minus 3 times 1. Negative, yep. Actually, hold on, let me go back real quick. So it's me 1 times 1 minus plus 3 times that. And then we get, oh yeah, so this is going to be plus, yeah. Plus, yeah. So it's going to be -4. Sorry about that. And then the k hat's going to be -2, -2 minus 3 is -5. So we have our vector, that's our direction vector that's normal to both these planes. And then we can now solve for our our values, right? And then in this case, if we were to actually sketch this out, which I think would have been useful for this problem, what you would see, in fact, is if you wanted, let's just do one of them, for example, real quick. So if we did x plus y minus z equals 2, if I had this, you could kind of envision that the plane would be going down to here and form like a triangle, like a tetrahedron of sorts, and you can envision the same thing with this. And in fact, the sketches on paper sketches on the iPad aren't as good as they would be on Desmos. If you feel free to look at Desmos as well, try and solve that. But the general idea is that when these vectors, when the planes intersect, that creates, it has to be normal to both of them. That's why the cross product is used to solve for that. And with that, we have to solve for the actual point, because we need to, with the line, we have to have a point that goes along with it, right? And in this case, I think the easiest thing for me, at least, is just to say z equals 0, because, like I said, that the planes are going to intersect, because these are both planes. Lines are 2D versions of planes. You're scaling them by including the z component, right? And if you set like z equal to 0, for example, what that really gets you is just a line in 2D, right? And then 3x minus 2y equals 3, excuse me. Let me just rewrite that. And in fact, what we can do now is just use we can use elimination to solve for our numbers for x and y to get our points. And then so we just add up these to be 5x equals 7, x equals 7 over 5. We plug it back into this original equation. So that means we know that y is going to be equal to 3/5. And now we have our point, 7 over 5, 3 over 5, 0. And then that's going to be our, let's just say call it r naught, not r naught, but the arrow, because it's not a vector, it's a point. Let me get to that. R of t equals this, and that's how you would solve for the line given to the planes. You would have to solve for the cross product, the resulting vector, and then you would also have to solve for a specific point on the plane. And for example, solving for z equals 0 is a way easier thing to do than, say, solving for like z equals like 10 or like whatever. You can set any of the variables equal to 0. I like to set z equal to 0 because in my head, at least, I'm still always stuck on lines being x and y, not x and z and y and z. And in this case, they technically all are the same thing, because we've never really thought of the third dimension as like being anything but anything like a line, be a plane. But you can still have lines in like the y and z plane, for example. You can write it as like z and y. You can still write it like that. It's technically still the same thing, but it's just not. It's not intuitive for us because we always imagine it in XY territory. And given this, we can try and solve for if the following lines are parallel, intersecting, or skew. And what this means is parallel means they have the same direction vector. So like if, for example, it was like 1, 1, 1, 1, 1, 1, they would be parallel because they have the same direction vector, so they would never touch each other. Intersecting means that at some point for some value of t and s, you would see that they would intersect, but that doesn't mean that their direction vectors are going to be the same, right? It's like, for example, having a line in space like this, just call this x plus 2, and we have something like this, negative 4/5 x plus 3. They're going to touch at some point. They're intersecting. They don't have the same slope. That would be like intersecting lines in 3D. And skew just means that they are never going to touch. In 2D, if we knew that two lines were never going to touch, that means we know that they're parallel. That means we know that the change in x or the change in y is the same for both. But in this case, we can't say that for sure. And now what we would have to do is we'd have to try and solve for our values of t and s. Let's see if they would be parallel, intersecting, or skew, right? And first off, we can try and set t and s equal to each other at a specific point. So I see that we have a constant here. We can try and see if they're going to match with this, right? So let's just say that 4 equals negative 3 minus 7s. It's going to be 4 equals, so it's going to be 7 equals negative 7s. So s equals negative 1. So then we can plug in the rest into here. We can see that's going to be 4, 1 times negative 4 is going to be negative 3, and 4 times negative 1 times negative 1 is 5. Okay. And then we can see that right here that 5 equals t plus 1. We can see that t equals 4, right, given this. So that means we can say that t equals, so we can say that t equals 4. We can plug it into here. 6 minus 4 equals 2, but this is 2, this is negative 3. Those do not correspond with each other, so therefore we can rule out the fact that it would be parallel. Intersecting would mean that at a specific point in space, they would have the same, they would have the same point shared in space, right? We can look for that given our direction vectors, and we can try and solve for that. Let's say what we can do actually is break this up into separate components, and we can do 4, 6, 1 as a point, because that's when t equals 0, as you can see for this, right? And then we can add in the other components, so it's going to be r arrow of t plus t of 0, negative 1, 1. And then we have big R of s equals, big R over s equals negative 3, 1, 4 plus s 1, negative 7, 4, negative 1, given at this specific point in space, right? And what we can do is we already solved for our s value, or to be negative 1, right? So what we can do now is try and solve for something else that they would have in common, right? So we know that s equals negative 1 is where they would meet there. And if we plug in negative 1 into here, let's see what we would get. We would get 4, -3. Wait, actually, 4, -3, and 4, -3, and then 4 minus -1 is 5. So that's what we got above. And then what we would do from here is see if there's a point that maps onto that for here. And we can try and solve for that. We can see when t is when t gets us -3, what value of t gets us -3, right? And t equals 3 would be that value, because it would be 6 minus 3 equals, actually no, not 6 minus 3, it would be, oh no, it would be 6 minus 3, because yeah, 6 minus 3, so that'd be 3, and it'd be 1 plus 4, which would get us 1 plus 3, oh sorry, 1 minus 3, excuse me, we get -2. So there would be 4 comma -3 comma -2. And then in that case, they wouldn't be intersecting. So therefore, these two lines are skew. And now we go to the more generalized version of curves in space. And you can look at this in the general form like this. We've already been using this kind of notation above, but it's still representative of that. And it's still true that F and G and H are defined in the interval from A to B, from tip to tail basically, but it's more generalized, not like from 0 to 1 or whatever like we were doing above. And in this case, you would also still write it as like t as an element from A to B. And you can see now that we have points across. It's not just going straight across, it's going up, it's going down, it's going left and right. And it's a more generalized version of what we've been doing. And now here are some examples from a textbook that we pulled. These are kind of difficult to sketch on paper. We can try, but it'd be better to visualize on Desmos. And we can look at this and see. So 4 cosine I. So these graphs always look a little bit funky, but the general gist is that it's going to look like a helix going up and up and up. And if you look at it straight down, in fact, it will look like a helix. It will look like an ellipse, with the x being 4 and the y being -1. I mean, the y being 1, excuse me. And if you looked at it from the side, it would just be like a sine wave oscillating up and down, oscillating up and down. Same thing for this roller coaster curve right here. It would give you the same thing, and then the slinky curve. I'm not going to graph those. Those are just some examples that you can pause the video and plug into Desmos and see what they look like, because they are really cool shapes that you can try. And also, if you're still stuck on these concepts, feel free to use Desmos as a tool to help you understand this, because what you can do on Desmos is you can look at specific axes, right? You can look at the XY plane, you can look at the YZ plane, the XZ plane, to understand how the shape looks like depending on if like Y is held constant or Z is held constant, right? And what we've been learning so far in Calculus 1 and 2, we've been holding Z constant the whole time, but now we're letting Z be free. And it's going to lead to a lot of cool opportunities. And this is something from Calc 1 that's going to pop up again later in Calc 3. It's just like the definition of like the derivative, right? It's pretty straightforward. And for example 5, you have to try and find the parametric equations of the tangent line to the curve x equals 2t squared, y equals 4t, and z equals 3t, t cubed at t equals 1. So we can try that. Just get our point first. It's going to be r of t equals 2 comma, oh no, sorry, has to be 2t squared 4t t cubed. And then we just solve for r of 2. So it's going to be 8, and, oh no, sorry, I was thinking t equals 2. It's going to be 2, 4, and 1 as a point in space. And then r prime of 2, this is the tangent line at t equals 1. Oh my gosh, t equals 1. I'm so sorry. This should be t equals 1. And we would get, this becomes 4t, this becomes 4, this becomes 3t squared. So this becomes 4, 1, and 3. So it becomes 4, 1, and 3. So then the tangent line would be negative 2, 4, 1 plus t, 4, 1, and 3 for r tangent of t. And then limits of continuity. This is straightforward Calc 1 stuff. So we can just do this real quick. So it'd be cosine of 2 pi is 1, sine of 2 pi is 0, e to the negative 2. And then for b, it's going to evaluate the limit as t approaches infinity for r of t. The issue is, though, is that we don't know if this is going to be oscillating from negative 1 and 1. So we're just going to say this is d and e, because we don't know. And at what point is r continuous? All 3 of these respective functions are continuous on the interval when t is greater than 0. So then we can just say that for all t on the interval, the parametric function is continuous. And that is pretty much it. Thank you for watching, and I hope you guys have a fantastic day.